What if everything you thought you knew about the universe was wrong? Imagine staring into the endless night sky, believing you understand the rules of reality, only to discover that the cosmos holds secrets so profound they unravel the very fabric of physics as we know it. At the heart of this cosmic enigma lies one of the most awe-inspiring and mysterious phenomena in existence: black holes. These aren't just distant curiosities, they are the ultimate cosmic paradoxes, regions where gravity becomes so intense that not even light can escape, where time and space behave in ways that defy every intuition we possess. They challenge our understanding of existence itself, pushing the boundaries of human knowledge into uncharted territories. Today, we're setting off on a journey to explore these magnificent cosmic giants, and we're going far beyond the basics. We'll uncover 30 astonishing facts about black holes, each one more mind-bending than the last, that will completely transform how you see the universe. From their mysterious origins to their shocking influence on the cosmos, these facts will reveal how black holes are not just destructive voids but dynamic engines that shape galaxies, warp the fabric of spacetime, and may even hold clues to the ultimate nature of reality. This isn't just a list of trivia, it's an invitation to rethink everything you thought was possible, to see the night sky not as a static painting but as a living, evolving story written in gravity and light. So prepare to have your perspective shifted in ways you never imagined. Whether you're deeply passionate about space or simply curious about the wonders of the cosmos, this exploration will leave you with a sense of awe and wonder, connecting you to the grand, mysterious dance of the universe. Let's begin this journey together and discover how black holes don't just hide in the darkness, they illuminate some of the greatest truths about existence itself. In fact, the very name black hole is one of the greatest misnomers in all of science. It conjures an image of a simple, empty void, a cosmic pothole in the fabric of space. But the reality is infinitely more fascinating and terrifying. A black hole is not an empty hole at all. Instead, it is the exact opposite, the most densely packed, massive object you can possibly imagine. Think of it this way. If you were to take an entire star, sometimes a star many times more massive than our own sun, and crush all of that immense matter down into a single, infinitesimally small point, you would create a black hole. This point is known as a singularity, a place where the laws of physics as we understand them break down completely. The density here is so incomprehensibly high that it warps the fabric of space and time itself, creating a gravitational pull so overpowering that nothing, not even light which travels at the universe's ultimate speed limit, can achieve escape velocity. What we perceive as the hole is actually the event horizon, the invisible boundary surrounding this singularity. This isn't a physical surface but a point of no return. Once anything, be it a planet, a spaceship, or a particle of light, crosses this threshold, it is irrevocably lost to the universe outside. So, rather than an empty pit, a black hole is a cosmic prison built from pure gravity, with an unimaginably dense inmate at its center, forever hidden from our view. This boundary, the event horizon, is perhaps the most haunting and defining feature of a black hole. It's the ultimate point of no return, a one-way door in the cosmos from which there is absolutely no exit. To grasp its true nature, you have to understand that it's not a physical, solid surface you could bump into. You wouldn't feel anything at all as you crossed it. Instead, it's a mathematical boundary in space, defined purely by gravity's irresistible grip. At the precise location of the event horizon, the escape velocity, the speed needed to break free of a celestial object's gravity becomes exactly equal to the speed of light. Since nothing in the universe can travel faster than light, nothing, not a single particle or shred of information, can ever make it back out. This is why black holes are black. Even light, the fastest thing there is, gets trapped and cannot travel to our eyes. But what would it actually be like to cross this threshold? the experience would be as strange as it is fatal. An outside observer watching you fall in would never actually see you cross the event horizon. From their perspective, your image would appear to slow down, becoming redder and dimmer as the light waves stretching to escape the intense gravity, until you faded from view entirely over an impossibly long time. For you, however, the trip would proceed quite rapidly. Once you cross that invisible line, the warping of spacetime becomes absolute. All possible paths, every direction you could possibly travel, no longer lead outward into the universe you came from. They all point inexorably forward in time, which now funnels directly toward the singularity at the center. It's like being in a river where the current suddenly becomes so powerful that every paddle stroke, no matter how hard, only pulls you faster toward the waterfall. You couldn't stop or change direction even if you had an infinite power engine. The very fabric of the cosmos ensures your fate is sealed. And this profound difference in perspective between an outside observer and someone falling in leads us directly to one of the most bizarre and terrifying physical processes in the entire cosmos. A phenomenon with a name that sounds almost comical but describes a fate of unimaginable horror: spaghettification. If you were ever to plunge toward a stellar mass black hole, being vaporized at the event horizon would be a merciful outcome compared to what would actually happen. The real danger isn't the singularity itself, but the extraordinary tidal forces you would encounter long before you ever reached it. To understand tidal forces, think of the ocean. The moon's gravity pulls on the side of the Earth facing it more strongly than the side facing away, and this difference stretches the oceans, creating high and low tides. A black hole takes this simple concept and amplifies it into a cosmic nightmare. Because its gravity is so unimaginably intense and concentrated, the difference in gravitational pull between one part of your body and another becomes catastrophic. If you were falling feet first toward a black hole, your feet would be just a few feet closer to the singularity than your head. But in the extreme gravity gradient near a black hole, that tiny distance makes all the difference. The gravitational pull on your feet would be exponentially stronger than the pull on your head. The result is a violent and irresistible stretching. You wouldn't just feel a tug, your entire body would be pulled lengthwise, as if you were a piece of taffy caught between two impossibly strong hands. You would be elongated, stretched out into a long, thin stream of atoms. At the exact same time, the incredible forces would also compress you from the sides, squeezing you inward from all directions. This combination of stretching and compressing is what transforms any object, be it a star, a spacecraft, or a person, into a terrifyingly thin strand of matter, a single, long string of atoms spiraling into the void. The process happens in mere fractions of a second, and it is as physically absolute as it is gruesome. You would literally become a human piece of spaghetti, your very atoms ripped apart and aligned in a line destined for the central singularity. It's a stark and visceral reminder that the universe operates by laws that are utterly indifferent to our existence, capable of producing wonders and horrors far beyond our earthly imagination. While the thought of spaghettification is a terrifying prospect for any would-be explorer, the true giants of the black hole world operate on a scale so vast it defies human comprehension. We've been talking about stellar mass black holes, the remnants of dead stars, but they are merely the minnows in a cosmic ocean ruled by leviathans. At the heart of nearly every large galaxy, including our own Milky Way, lies a sleeping monster, a supermassive black hole. These are not simply larger versions of their stellar cousins. They are a different class of object entirely, with masses ranging from millions to tens of billions of times that of our Sun. Our own galactic center is home to one such behemoth, known as Sagittarius, a star. While it is currently quiet and relatively inactive, its presence is undeniable, its gravitational weight equivalent to 4 million suns all crushed into a single point of unimaginable density. The existence of these supermassive black holes is no mere coincidence. It appears to be a fundamental rule of cosmic architecture. The correlation is so strong that astronomers now believe the evolution of a galaxy and the growth of its central black hole are inextricably linked in a complex symbiotic dance. One of the most compelling theories suggests that these black holes act as the ultimate cosmic regulators. In the early, chaotic universe, as galaxies were forming from vast clouds of gas and dust, the supermassive black hole at the center would feast on this abundant material. As matter spiraled in, it would form a superheated accretion disk, blazing with the energy of a billion stars and becoming what we call a quasar. The incredible radiation and powerful jets of particles blasting out from this process would literally blow away the surrounding star-forming gas, effectively putting a brake on the galaxy's growth. In this way, the black hole, by devouring the very material that feeds it, ultimately determines the final size and structure of its host galaxy. It's a fascinating feedback loop. The galaxy provides the food, and the black hole, in its violent feasting, decides when the meal is over. This relationship explains why we don't see endlessly growing galaxies, and suggests that these dark giants are not just silent occupants, but were once the active, brilliant hearts that shaped the cosmic landscape we see today. But if gravity alone were the full story of a black hole, we would be missing one of its most dynamic and astonishing features. You see, black holes aren't just static, featureless pits in space. Many of them are cosmic whirlpools, spinning at velocities that push the very limits of physics itself. When a massive star collapses to form a black hole, it doesn't just lose its mass, it also preserves its angular momentum. Think of an ice skater pulling their arms in during a spin. Their rotation speeds up dramatically as they become more compact. Now imagine that on a cosmic scale. A star that may have rotated once every few weeks can, upon collapsing into a black hole just a few miles across, spin up to a significant fraction of the speed of light. We're talking about complete rotations hundreds of times every single second. This isn't just a trivial detail. This spin fundamentally changes the black hole's nature and its interaction with the universe. This incredible rotation warps the fabric of spacetime around it in a profound way, a phenomenon predicted by Einstein's theory of general relativity known as frame dragging. Imagine spacetime not as a static stage but as a vast, viscous fluid. A non-spinning black hole is like a heavy ball sitting motionless on that fluid, creating a deep indentation. But a spinning black hole is like that same ball now being spun rapidly. It doesn't just create a dent, it drags the entire fabric of the fluid around with it. Anything that gets near a spinning black hole, light, dust, even space itself, is caught in this cosmic whirlpool and forced to rotate along with it. There's a region outside the event horizon called the ergosphere, where resisting this drag is literally impossible. Every object and every bit of space within this region is compelled to move in the direction of the spin. It's a tangible demonstration that space and time are not just a backdrop for the universe's events, but are active, dynamic participants that can be twisted and pulled by immense forces. This spinning motion also dramatically alters the black hole's anatomy. A non-spinning or Schwarzschild black hole has a perfectly spherical event horizon. But when rotation is introduced, that horizon changes shape. The centrifugal force generated by the incredible spin causes the black hole to bulge at its equator, much like our own Earth, creating an oblate spheroid, a sphere that's flattened at the poles and stretched at the middle. The faster it spins, more pronounced this deformation becomes. Furthermore, the spin dictates the size of the event horizon itself. For a black hole spinning at the maximum possible rate, the event horizon's radius can be half that of a non-spinning black hole of the same mass. This creates a fascinating situation where the point of no return is actually closer to the center, all because of the immense rotational energy contained within. And it is this stored energy that presents one of the most thrilling possibilities in all of theoretical physics. The ergosphere, that region of forced rotation, isn't just a curiosity. It's a potential power plant of unbelievable magnitude. A theory proposed by physicist Roger Penrose suggests that we could, in principle, extract energy from a spinning black hole. Here's how this astonishing process could work. If an object were to fly into the ergosphere and split into two parts, with one piece falling past the event horizon and the other escaping, the escaping fragment could actually emerge with more energy than the original object had when it entered. The infalling piece has negative energy relative to the outside universe, and to balance the books, the ejected piece gains a tremendous amount of kinetic energy. This means we would be stealing rotational energy from the black hole itself, causing it to spin down slightly. It's a concept that transforms the black hole from a simple consumer of matter and energy into a dynamic cosmic engine, a battery from which advanced civilizations might one day draw power. This isn't just science fiction, it's a direct consequence of the mind-bending physics that governs these incredible spinning giants. Yet for all their immense power and spinning fury, black holes have long been thought to possess one absolute, unchanging trait: their permanence. Once formed, the classical laws of physics dictated that a black hole could only grow, steadily accumulating mass and energy from everything that fell in, with no possible mechanism for it to lose even a single particle. They were seen as the ultimate endpoints of entropy, eternal prisons from which nothing, not even information, could ever be retrieved. This notion was so entrenched that it was simply how the universe worked, until one brilliant mind turned this idea on its head and revealed that even these cosmic titans are subject to the strange and counterintuitive laws of quantum mechanics. Stephen Hawking's revolutionary work showed us that black holes are not truly black, and they are not eternal. Hawking's insight was to ask a profound question: what happens when you apply the bizarre rules of the quantum world to the edge of a black hole's event horizon? In the seemingly empty vacuum of space, quantum physics tells us that pairs of virtual particles are constantly flickering in and out of existence everywhere all the time. These are particle-antiparticle pairs that borrow energy from the universe for an impossibly brief moment before they inevitably collide and annihilate each other, paying the energy back. This is not just a theoretical idea, it's a well-documented phenomenon with real effects like the Casimir effect. Normally, this creation and destruction happens in perfect balance with no net energy being produced. But Hawking realized that near the event horizon of a black hole, this delicate balance can be catastrophically broken. Imagine one of these virtual particle pairs popping into existence right at the precipice of the point of no return. There's a chance that one particle will fall on the wrong side of the line, plummeting past the event horizon and into the black hole, while its entangled partner is left outside, suddenly free from annihilation. With its partner lost forever to the singularity, the escaped particle can no longer return the energy it borrowed. It becomes a real particle, and it carries real energy away from the black hole as it flies off into space. To an outside observer, this stream of escaping particles looks exactly like thermal radiation, heat being emitted from the black hole itself. This is Hawking radiation. The implications of this are staggering. First, it means black holes are not the perfect black bodies we thought they were. They have a temperature and they glow, albeit incredibly faintly. Second, and more profoundly, this process has a cost. The particle that fell into the black hole didn't just vanish, it had negative energy relative to the outside universe. When it joins the black hole, it effectively reduces the black hole's total mass and energy by a tiny, almost imperceptible amount. So, while the black hole is emitting radiation and losing mass, it is not actually emitting the matter that fell into it eons ago. Instead, it is evaporating, slowly converting its own immense mass into a faint drizzle of particles over timescales that are almost impossible to comprehend. For a stellar mass black hole, the temperature of this Hawking radiation is incredibly cold, just a tiny fraction of a degree above absolute zero. because the radiation is inversely related to the black hole's mass. The larger the black hole, the colder it is and the slower it evaporates. A black hole with the mass of our Sun would take an unimaginable 10 to the 67 years to evaporate, a number so vast it exceeds the current age of the universe by many orders of magnitude. But for a much smaller, hypothetical black hole, say, one the mass of a mountain, the story is very different. It would be incredibly hot, glowing with intense radiation, and would evaporate in a spectacular flash of energy in just a fraction of a second. This revelation completely reshaped our understanding of black holes, transforming them from eternal gravitational traps into dynamic, evolving objects with a life cycle that ends not with a bang, but with a silent quantum whisper. But Hawking's brilliant solution to one cosmic riddle inadvertently created another, one so deep and troubling that it has divided physicists for decades and strikes at the very heart of whether the universe is fundamentally knowable. This is the infamous black hole information paradox, and it remains perhaps the greatest unsolved puzzle in all of theoretical physics. To understand why it's so paradoxical, we have to start with one of the most sacred principles in quantum mechanics, the conservation of information. In our everyday lives, we're used to information being fragile. You can burn a book and turn its carefully arranged words into meaningless ash and smoke. But the laws of quantum physics insist that on a fundamental level, this is an illusion. The information that made up that book, the specific arrangement of all its atoms and the energy states that encoded the letters, is not actually gone. In principle, if you could somehow track every single ash particle, every photon of light, and every bit of heat emitted from the fire, you could reverse the process and reconstruct the book perfectly. Information, in the quantum sense, is never truly destroyed. It can only be scrambled into a form that is incredibly difficult, perhaps practically impossible, to decode. It's a fundamental tenet that the universe always keeps perfect records. Now enter the classical black hole as described by Einstein's general relativity. It is the ultimate shredder. If you throw that same book into a black hole, it is gone. The book crosses the event horizon, is spaghettified, and its matter and energy are added to the mass of the black hole. According to classical theory, the only properties a black hole has are mass, electric charge, and spin. It has no hair, as physicist John Wheeler poetically put it, meaning it retains no other details about what fell in. A black hole made from 100 books and a black hole made from 100 stars with the same total mass are completely identical. The information about what each was made of is utterly lost, erased from the universe. This directly violates the quantum law that information must be preserved. Initially, Hawking radiation seemed to make this problem infinitely worse, not better. Hawking's calculations showed that the radiation emanating from a black hole is purely thermal. It's random noise, like the static from a detuned radio, containing no information whatsoever about the intricate objects that fell in. So, as the black hole evaporates over eons, it eventually vanishes completely, leaving behind nothing but this featureless, random haze of particles. The inevitable conclusion seemed to be that all the information about everything that ever fell into that black hole, every book, every planet, every person, is irrevocably lost to the universe. This creates a catastrophic paradox because quantum mechanics and general relativity, the two pillars of modern physics, give us two completely contradictory answers about reality, and both cannot be true. It suggests our fundamental understanding of the universe is broken at the most basic level. The scientific community has been grappling with this for decades, and several compelling, albeit strange, solutions have been proposed. One prominent idea is that the information isn't actually lost, it is somehow encoded on the event horizon itself. The holographic principle suggests that all the information about things that fell into the three-dimensional volume of the black hole could be perfectly preserved on the two-dimensional surface of its event horizon, like a cosmic hologram. Then, as the black hole evaporates via Hawking radiation, this information is slowly and subtly imprinted onto the outgoing radiation particles. It wouldn't be obvious, the information would be scrambled into what looks like random noise, but in principle, it would be there for a sufficiently advanced physicist to decode. This would satisfy quantum mechanics by preserving information, but it requires a mechanism that we don't yet fully understand within the framework of general relativity. Another, even more radical proposal is that black holes don't have a true interior at all. The firewall hypothesis suggests that instead of an empty space inside the event horizon leading to a singularity, the event horizon itself might be a blazing wall of unimaginably high energy particles. Anything hitting this firewall would be instantly incinerated, and its information would be transformed into energy right at the horizon. This idea solves the information paradox by preventing anything from ever actually falling in and having its information lost, but it does so by violently violating Einstein's principle of equivalence, which states that an observer falling into a black hole should not notice anything special as they cross the event horizon. It trades one paradox for another. The resolution to this puzzle is so elusive because it likely requires a theory of quantum gravity, a way to seamlessly merge the laws of the very small quantum mechanics with the laws of gravity and the very large general relativity. The information paradox is the glaring symptom that these two theories, while brilliant and powerful on their own, are incomplete. Unifying them will force us to rewrite our understanding of spacetime, information, and reality itself, revealing a universe far stranger and more wonderful than we ever imagined. This incredible distortion of spacetime doesn't just affect the paths objects can take, it fundamentally warps the very flow of time itself. One of the most profound predictions of Einstein's theory of general relativity is that gravity doesn't just bend space, it also slows down time. The stronger the gravitational field, the more time dilates or stretches out compared to a weaker field. Nowhere in the universe is this effect more extreme than at the precipice of a black hole. Imagine two identical clocks, both perfectly synchronized. If you were to courageously take one clock and fly it on a mission toward a black hole while your friend stayed far away with the other, something utterly bizarre would happen. From your friend's perspective, watching from a safe distance, the clock near the black hole would appear to tick slower and slower the closer it got to the event horizon. For you, holding the clock on your doomed journey, time would feel perfectly normal. Your watch would tick at its usual rate, and your thoughts would process at their normal speed. But your friend would see your entire existence slowing to a crawl. This time dilation becomes infinite at the event horizon itself. From the outside universe's point of view, an object falling into a black hole never actually crosses the event horizon. As it approaches that ultimate boundary, its descent appears to slow down more and more, its image becoming redder and dimmer due to the light struggling to escape the intense gravity, a phenomenon called gravitational redshift. The object would appear to hover, frozen in time and space, forever etched onto the surface of the black hole from the perspective of a distant astronomer. This isn't an optical illusion, it is a direct consequence of the extreme warping of spacetime. Time, for that infalling object, has effectively stopped relative to the rest of the universe. Of course, from the object's own perspective, time continues unabated, and it would cross the event horizon and meet its fate at the singularity in a finite amount of time. This creates a universe of two simultaneous, yet completely different realities. A stark reminder that time is not the universal constant we experience in our daily lives, but a flexible dimension that is intimately woven into the fabric of space and shaped by gravity. This astonishing range of black holes reveals a cosmic family far more diverse than we once imagined. For a long time, astronomers primarily knew of two extremes, the stellar mass black holes and the supermassive ones. But the universe, in its infinite creativity, fills in the gaps with objects of every conceivable size. The smallest among them are the stellar mass black holes, the ones we've discussed forming from the collapse of massive stars. These typically range from about 3 to 100 times the mass of our Sun, all crushed into an area no wider than a large city. While their size is modest by cosmic standards, their density is anything but. A single teaspoon of matter from one would weigh billions of tons here on Earth. The true giants, of course, are the supermassive black holes, behemoths with masses starting in the millions and soaring into the tens of billions of solar masses. Their physical size is equally mind-boggling. The event horizon of Sagittarius, a star, our own galaxy's 4 million solar mass black hole, would stretch about 1/4 the distance from the Sun to Mercury. The supermassive black hole at the heart of the galaxy M87, famously photographed, has a mass of 6.5 billion suns, and its shadow cast against glowing gas is larger than our entire solar system. These are not just objects, they are gravitational anchors around which entire galaxies spin. For decades, a puzzling gap existed between these two classes. Where were the middleweight black holes? Theorists predicted their existence, black holes with masses between 100 and 100,000 suns, but finding them proved difficult. These intermediate mass black holes are thought to be the missing link, the seeds that could grow into supermassive monsters by merging with others and devouring gas over billions of years. Excitingly, we are now finding them. Evidence points to their existence in the dense hearts of some globular clusters and in the midst of certain dwarf galaxies. Some astronomers believe the mysterious gravitational wave signal known as GW190521, which came from the merger of two objects, might have been the birth cry of an intermediate black hole, providing a crucial piece of the cosmic puzzle. Perhaps the most mysterious members of the black hole family are the hypothetical primordial black holes. These are not born from dying stars but are thought to be fossils from the universe's explosive birth. In the first frantic fraction of a second after the Big Bang, when the cosmos was a seething, dense soup of energy, tiny fluctuations in density could have collapsed under their own weight, punching holes in the fabric of spacetime itself. These primordial black holes could have any size, from the mass of a mountain to many times that of our Sun. Some theories even suggest they could be microscopic, with the mass of an asteroid compressed into a size smaller than an atom. If they exist, these tiny, ancient black holes could be buzzing through our solar system, even through the room you're in right now, virtually undetectable. Some scientists have even proposed that one of these could be the elusive planet 9 influencing orbits in our outer solar system, or that they could make up a portion of the universe's mysterious dark matter. Their potential existence opens a window into the very first moments of everything, a ghostly echo of creation itself. Yet for all their solitary majesty, black holes are not destined to exist in isolation forever. In the grand cosmic dance, they often find partners, leading to the most violent and energetic mergers in the universe. When two black holes are locked in a mutual orbit, drawn together by their immense gravity, they begin a long, slow spiral toward an inevitable collision. This process can take millions of years as they slowly lose energy by stirring up the fabric of spacetime itself. As they draw closer, their orbital speed increases to a significant fraction of the speed of light, whirling around each other hundreds of times per second in a final, furious dance. The forces involved are beyond comprehension. Here you have two of the most extreme objects in existence, each containing the mass of multiple stars compressed into an infinitesimal point, now circling each other at incredible velocities. In the final moments before the merger, the system releases more energy than all the stars in the observable universe combined. But this energy isn't released as light or radiation. It is emitted in a form that was, until very recently, entirely theoretical, gravitational waves. Predicted by Einstein's theory of general relativity, gravitational waves are ripples in the very fabric of spacetime itself. Think of spacetime as a taut rubber sheet. When a massive object like a black hole moves through it, it creates waves, much like a boat moving across the surface of a lake. These ripples propagate outward at the speed of light, stretching and compressing everything in their path as they travel across the cosmos. During a black hole merger, the intense, accelerating motion of these colossal masses creates a tsunami in spacetime, a powerful wave that carries away a portion of the system's energy. The finale of this cosmic event is the actual merger. The two black holes, after their final frantic orbits, collide and become one. The new, single black hole is initially highly distorted, a misshapen blob of pure gravity, but it quickly settles down to a stable state through a process called ring-down, shedding its imperfections in a final burst of gravitational waves. The amount of energy converted into pure spacetime ripples in this event is staggering. For example, the first merger ever detected converted roughly 3 times the mass of our Sun directly into energy in the form of gravitational waves in a fraction of a second. To put that in perspective, that is more energy than has been emitted as light by every star in the universe over that same brief moment. It is the single most powerful event humans have ever witnessed. For decades, gravitational waves remained a brilliant prediction, but their direct detection seemed nearly impossible because their effect on Earth is so infinitesimally small. That all changed in 2015 with the Laser Interferometer Gravitational Wave Observatory, or LIGO. This incredible instrument consists of 2 facilities, one in Louisiana and one in Washington state, each with 2 4-kilometer-long arms arranged in an L shape. A laser beam is split and sent down each arm, reflected back by mirrors, and then recombined. When a gravitational wave passes through Earth, it minutely changes the length of the arms. One arm stretches while the other compresses, by a distance 1,000 times smaller than the nucleus of an atom. This tiny change alters the pattern of the recombined laser light, signaling the passage of a wave. On September 14, 2015, LIGO detected its first signal, designated GW150914. It was the ripple from 2 black holes, one about 36 times the mass of the Sun and the other 29, merging over 1.3 billion light-years away. The signal, a characteristic chirp that rose in frequency and amplitude as the black holes spiraled inward, was a perfect match for Einstein's predictions and marked the dawn of a new era in astronomy. Since then, LIGO and its European counterpart, Virgo, have detected dozens of these events, each one a silent testimony to a cataclysm of unimaginable scale happening in the dark reaches of space. We are no longer just observers of the cosmos. We are now listeners, tuning in to the vibrations of spacetime itself to hear the universe's most powerful events. Perhaps the most persistent and dramatic misconception about black holes is the idea that they act as relentless cosmic vacuum cleaners, endlessly sucking in everything around them in a terrifying, inescapable whirlpool of destruction. This image is a staple of science fiction, but it bears little resemblance to reality. The truth is far more nuanced and in many ways more fascinating. Black holes do not possess some magical, extra-powerful suction force that reaches out across space to grab things. Their gravity operates by the exact same rules as any other object in the universe. The force of attraction is determined by their mass and your distance from them. Think of it this way: if our Sun were to be instantly, magically replaced by a black hole of exactly the same mass, a terrifyingly quiet event would unfold. The Earth and all the other planets in our solar system would not be instantly pulled inward and devoured. Why? Because the gravitational source at the center of our solar system would still have the exact same mass. Our orbit would remain completely unchanged. We would continue to revolve around that point of absolute darkness, locked in the same elliptical path we've followed for billions of years. The major difference, of course, is that the warmth and light that sustains life on Earth would vanish, plunging us into a permanent, frozen night. The doom would come from the cold and dark, not from being spaghettified. This reveals a crucial principle. For any object to be captured by a black hole, it must come perilously close to it, venturing inside a region where the orbital velocity required to maintain a stable path exceeds the speed of light. Until that point, objects can and do orbit black holes perfectly safely. We see this spectacularly in the center of our own galaxy. Astronomers have tracked stars like the famous star S2, racing on incredibly fast elliptical orbits around Sagittarius, a star. They whip around at thousands of kilometers per second, coming within a breathtakingly close 17 light hours of the event horizon, a cosmic near miss by any standard, only to swing back out again, completely unharmed by their encounter. Their orbits are a perfect demonstration of Kepler's and Newton's laws of motion, playing out exactly as they would around any other massive object. The vacuum cleaner myth likely stems from visualizing a black hole as a literal hole or drain in space. But it's more accurate to think of it as an incredibly deep and steep gravitational well. A marble rolling on a flat sheet might travel in a straight line, but if you place a bowling ball on that sheet, it creates a dip. The marble will curve its path because of the indentation. Now, imagine a well so infinitely deep and steep that its sides are vertical. That's a black hole. An object can roll around the outer, gently sloping edges of this well indefinitely, just as planets orbit a star. It's only if that object's path takes it over the sheer, vertical cliff of the event horizon that it is lost forever. Black holes don't reach out and pull, things have to fall in. Their terrifying power is passive, not active, governed by the same universal laws that keep the moon in orbit around our planet. Yet for all the immense power and drama of their outer boundaries, the true, ultimate mystery of a black hole lies concealed at its very heart, hidden behind the event horizon's final curtain. This is the singularity, a concept so alien to our understanding of reality that it represents the absolute frontier of human knowledge and the ultimate breakdown of physics as we know it. If you were somehow able to survive the journey inward, passing through the event horizon and enduring the tidal forces, you would eventually arrive at the black hole's core. But you wouldn't find a solid surface, a ball of exotic matter, or any structure you could recognize. According to the equations of general relativity, you would find a point of infinite density and zero volume, a singularity. This isn't just an object being very small or very dense. It is a place where the familiar rules of the universe cease to function. The curvature of spacetime caused by the immense concentration of mass becomes infinite itself. The very fabric of reality is warped to a point where the concepts of here and now lose all meaning. In this state, the gravitational field and the energy density reach values that are not just large but literally undefined by mathematics. Our current theories of physics, which have so brilliantly described the cosmos from the quantum scale to the galactic, simply throw up their hands in surrender. They return answers of infinity, which in the language of physics is not an answer at all. It's a glaring sign that the theory has reached its limits and broken down. This presents science with a profound and humbling dilemma. The existence of a singularity is essentially a message from the universe telling us that our picture of reality is incomplete. General relativity, Einstein's magnificent theory of gravity, is a classical theory. It describes the force of gravity as the curvature of a smooth, continuous spacetime. But it doesn't account for the bizarre, probabilistic rules of the quantum world that govern the behavior of matter at the very smallest scales. The singularity is where the immense gravity of the classical world demands that we include quantum mechanics, but we currently lack the framework to successfully marry these two pillars of modern physics. A theory of quantum gravity, which physicists have been seeking for decades, would be needed to truly describe what happens at the center of a black hole. This quest has given rise to several fascinating proposals that attempt to peer beyond the classical singularity. One leading idea comes from string theory, which suggests that what we perceive as a point of infinite density might actually be a tiny, vibrating loop of energy, a fundamental string. In this view, there is no true singularity, as the string has a finite size, preventing the infinities from arising. Another compelling concept is the Planck star from loop quantum gravity, which proposes that at the very core, the immense gravitational collapse actually reverses due to quantum effects, causing a bounce that could theoretically lead to a new universe or a different region of spacetime. These ideas are highly speculative, but they represent the courageous effort to push beyond the known and explore what might lie at the very edge of existence. Ultimately, the singularity is either a fundamental limitation of our current models or a gateway to a new, deeper understanding of the cosmos. It forces us to confront the fact that our knowledge, for all its power, is provisional. The universe is under no obligation to conform to our human intuition or our mathematical elegance. The mysterious heart of a black hole stands as the ultimate challenge, a cosmic puzzle waiting for its Einstein to one day unlock its secrets and reveal a new chapter in our understanding of reality itself. But this incredible gravitational energy is only half the story of a quasar's power. The other half lies in the mind-bending efficiency of the process itself. When matter falls into a black hole, it doesn't just vanish quietly. It converts a staggering portion of its mass into pure energy. To put this in perspective, consider the process of nuclear fusion that powers our sun. It is incredibly powerful, fusing hydrogen into helium and converting about 0.7% of the mass involved into energy, as described by Einstein's famous equation, E equals mc squared. This is what has sustained life on Earth for billions of years, but the accretion disk around a supermassive black hole operates on a completely different level. The friction, magnetic fields, and sheer violence of the infall can convert up to 40% of an object's mass into energy as it spirals inward. This makes it hundreds of times more efficient than fusion, the most powerful engine known to science. A single star falling into such a black hole can release more energy than an entire galaxy of normal stars shining for millions of years. This is why a quasar, which is essentially a single point of light smaller than our solar system, can outshine a galaxy containing hundreds of billions of stars. It is the ultimate cosmic powerhouse, a testament to the unbelievable energies that can be unleashed when the universe's most extreme objects engage in a violent feast. Now, if we shift our gaze from the raw destructive power of these objects to the subtle effects they have on the fabric of the cosmos, we find one of their most elegant and scientifically valuable traits. The immense gravity of a black hole doesn't just trap things that come too close. It also acts like a cosmic lens, warping the very path of light itself in a phenomenon known as gravitational lensing. This isn't some exotic, rare event. It's a direct prediction of Einstein's general relativity, which tells us that mass curves spacetime and light must follow that curvature. A black hole, with its incredible density, creates one of the most profound curves imaginable. Imagine a bowling ball placed on a taut rubber sheet. It creates a deep, steep-sided well. Now, if you were to roll a marble past the edge of that well, its path would bend inward, curving around the depression. Light behaves in exactly the same way as it travels through the warped spacetime around a massive object. It doesn't get sucked in by the gravity. Its straight-line path through the universe is simply bent because the space it is moving through is itself bent. When this lensing object is a black hole, the effects can be truly spectacular and incredibly useful for astronomers. Depending on the alignment between the black hole, Earth, and a distant background object like a galaxy or quasar, several breathtaking optical effects can occur. In a perfect, precise alignment, we might see an Einstein ring. This is a complete circle of light, a halo formed when the light from the background object is smeared and stretched around the black hole in a perfect ring. It's a beautiful and rare confirmation of the geometry of the universe. More commonly, the alignment is slightly off, and we see multiple images of the same background object. The black hole's gravity effectively creates multiple paths for the light rays to travel to reach our telescopes. Some light that would normally have shot off into deep space is bent around the sides of the black hole and redirected toward us, creating duplicate and often magnified copies of the same galaxy or star. These cosmic mirages can appear as distinct, distorted arcs or mirrored images clustered around the invisible lens. For scientists, this is far more than just a pretty picture, it's a powerful tool. By carefully studying the distortion, the shape, brightness, and number of these multiple images, astronomers can perform something called gravitational lens mapping. They can literally weigh the black hole causing the lensing, calculating its mass with remarkable precision based on how severely it bends the light. It's one of the most direct ways we have to measure the mass of these invisible objects. Furthermore, this natural telescope amplifies the light from incredibly faint, distant galaxies that would otherwise be far beyond the reach of our largest man-made observatories. A black hole's gravity can act as a magnifying glass, allowing us to peer deeper into the early universe than we ever could on our own, studying the formation of the first galaxies and the nature of the cosmic expansion. So, a black hole, often seen as the ultimate symbol of darkness and oblivion, also serves as a brilliant cosmic lighthouse, illuminating the secrets of the universe that lies behind it. Yet while black holes are masters of bending light and energy on a cosmic scale, some of the most intriguing possibilities involve objects that might be hiding in plain sight, so small and dark that they have eluded our detection for decades. This brings us to one of the most compelling and controversial ideas in modern cosmology, the possibility that black holes themselves could be the mysterious substance we call dark matter. For years, the evidence for dark matter has been overwhelming. We see galaxies rotating so fast that they should fly apart. We observe the gravitational lensing effects of unseen mass, and we map the large-scale structure of the universe, all pointing to the existence of about 5 times more matter than we can see. But what is this invisible stuff? The leading candidates have been various exotic particles like WIMP or actions that have so far escaped our most sensitive detectors. But another hypothesis, once considered fringe but now experiencing a major revival, suggests that at least a portion of dark matter could be made of black holes. Not the giant ones we've been discussing, but trillions upon trillions of ancient primordial black holes. These wouldn't be the black holes born from dying stars. Instead, they would be fossils from the universe's explosive birth, forming in the first chaotic fraction of a second after the Big Bang. During this incredibly hot, dense phase, tiny random fluctuations in density could have been amplified by the rapid expansion of the cosmos. In some regions, matter could have been packed so tightly that it collapsed directly under its own weight, punching tiny holes in the fabric of spacetime itself. This process could have created black holes of virtually any size, from ones with the mass of a small moon to others weighing as much as 1,000 suns. Crucially, because they formed before the first stars ever ignited, they are truly primordial, ancient relics wandering the cosmos for nearly 14 billion years. The appeal of this idea is its elegant simplicity. It doesn't require us to invent new, never-before-seen particles. It only requires that the conditions in the very early universe allowed for these collapses to happen. If a significant number of these primordial black holes were created and they have survived to the present day, they would be everywhere, drifting through interstellar space, lurking in the halos of galaxies, and yes, even passing through our solar system. They would emit no light, they would rarely accrete enough gas to be seen, and their only interaction with the rest of the universe would be through their gravity. In other words, they would behave exactly like dark matter, but a compelling hypothesis must withstand rigorous scrutiny, and this one faces significant challenges. The first major constraint comes from microlensing surveys. The idea is that if a population of massive, planet-sized primordial black holes were common in the halo of our galaxy, they would occasionally pass directly between Earth and a distant star. Their gravity would act as a tiny lens, briefly magnifying the star's light in a predictable way. Extensive projects like the Macho and Eros collaborations spent years monitoring millions of stars in the Large Magellanic Cloud, looking for these telltale flashes. They found a handful of candidate events, but nowhere near enough to account for all the dark matter we know must be there. This effectively ruled out the possibility that all dark matter is made of black holes in the mass range of large planets to about 100 solar masses. However, the story doesn't end there. The window is still wide open for black holes, both much smaller and much larger. On the smaller end, black holes with masses similar to a large asteroid could be incredibly numerous and would be too small to create a detectable microlensing signal. On the much larger end, black holes of hundreds or thousands of solar masses would be so rare that our surveys simply haven't looked at enough stars for long enough to have a chance of catching one lensing an event. Furthermore, the incredible success of LIGO and Virgo in detecting gravitational waves from merging black holes has thrown a fascinating new piece of evidence into the mix. Many of the black holes they've found are in the 20 to 50 solar mass range, which is heavier than what standard stellar evolution models typically predict. This has led some scientists to wonder if at least some of these could be primordial black holes, ancient objects that have been drifting through space since the beginning of time, occasionally finding each other and merging. The possibility remains an open and active field of research. Future gravitational wave observatories like the space-based LISA mission will be sensitive to mergers of much larger black holes, potentially uncovering a hidden population of these intermediate mass primordial objects. Other methods, like looking for the distinct gravitational wave background they would create, or searching for the subtle effects they would have on the cosmic microwave background, are also underway. While it's unlikely that primordial black holes are the sole answer to the dark matter enigma, they could very well be a piece of the puzzle, a hidden, gravitational component of the cosmos that has been with us since the very first moments of everything. Yet for all their complexity and terrifying power, classical physics presents us with a profoundly simple and almost poetic description of a black hole's final state. This is the essence of the famous no-hair theorem, a cornerstone of our understanding for decades. In the stark, elegant world of general relativity, a black hole that has settled down after its formation is the ultimate minimalist object. It is completely and utterly defined by just three numbers: its mass, its electric charge, and its spin. Nothing else matters. It doesn't matter if the black hole was formed from a collapsing star made of pure hydrogen or one laced with iron. It doesn't remember if it swallowed 1,000 planets, a library of books, or a fleet of alien spaceships. All of that intricate, rich information about its history and composition is irretrievably lost. The black hole sheds all of its distinguishing features, all of its hair, leaving behind a perfectly smooth, featureless gravitational field. As physicist John Wheeler succinctly put it, a black hole has no hair. This means that if you were to encounter two black holes with identical mass, charge, and spin, you would have absolutely no way of telling them apart. They are cosmic identical twins, their pasts erased by the ultimate gravity of the situation. This beautiful simplicity, however, creates a monumental clash with another fundamental pillar of physics, quantum mechanics. Quantum theory insists that information cannot be truly destroyed. The specific quantum states of all the particles that fell into the black hole must in principle be preserved. If information were truly lost, it would violate the unitarity of quantum mechanics, essentially breaking the predictability of the universe at its most basic level. This conflict is the heart of the black hole information paradox we discussed earlier, and it has forced physicists to ask a daring question. Is the no-hair theorem actually correct, or could black holes have some subtle quantum form of hair after all? Recent theoretical breakthroughs suggest that the latter might be true. The quest to resolve the information paradox has led to fascinating proposals that black holes do, in fact, retain information about what fell into them, but in a way that's incredibly subtle and woven into the very fabric of their being. One compelling idea is that this information isn't stored inside the black hole, but is instead encoded on its surface, the event horizon. The holographic principle suggests that all the information about the three-dimensional volume of the black hole is perfectly preserved as a two-dimensional hologram on its boundary. In this view, the event horizon is not a smooth, featureless surface. At a quantum level, it is a seething, chaotic tapestry of fluctuating energy, with each tiny plank-sized area acting as a bit of information. When an object falls in, it doesn't vanish. It merely adds its information to this incredibly complex and scrambled pattern on the horizon's surface. The black hole would then slowly release this information, imprinted in the correlations between the particles of Hawking radiation as it evaporates. This would be a new quantum form of hair, not a classical property like mass, but a detailed, information-rich structure that preserves the history of the black hole. Other challenges to the pure no-hair theorem come from the study of exotic fields. Theories that extend the standard model of particle physics often predict the existence of new, fundamental fields. If these fields exist, they could interact with a black hole in a way that gives it a new measurable property. For instance, a black hole could potentially support a cloud of a light scalar field around it, creating a gravitational atom of sorts. This cloud would create a subtle but potentially detectable deviation in the black hole's gravitational field, a new kind of hair that goes beyond mass, charge, and spin. The ongoing detection of gravitational waves provides us with a powerful new tool to test these ideas. By exquisitely measuring the gravitational wave signals from merging black holes, scientists can look for tiny deviations in the signal that might hint at the presence of such quantum hair or other beyond standard model physics. The ringing of the new black hole as it forms its ring down is like a fingerprint. If that fingerprint shows even the slightest feature that cannot be explained by just mass and spin, it would be revolutionary evidence that black holes are not the simple, bald objects of classical theory, but are in fact far more complex and information-rich than we ever dreamed. But even as a black hole is the universe's most efficient consumer, it is also capable of becoming its most powerful engine, capable of launching matter across intergalactic space in one of the most spectacular displays of cosmic force. While we picture black holes as the ultimate endpoints for matter, the reality is far more dynamic. Some of the most energetic black holes don't just pull things in, they also fire colossal beams of matter and energy back out into the cosmos at velocities approaching the speed of light. These are relativistic jets, and they are among the most awe-inspiring phenomena in the universe. They don't come from the black hole itself, nothing can escape from within the event horizon, but from the frenzied maelstrom of its accretion disk. As matter spirals inward at tremendous speeds, it doesn't just heat up, it also generates unbelievably powerful magnetic fields that become twisted and wound up by the black hole's immense rotation. Think of it like twirling a rope. The faster you spin, the more tightly the strands coil and the more tension builds up. Near the poles of the spinning black hole, where the magnetic field lines are funneled into a tight, focused beam, this built-up energy finds its escape route. Some of the infalling material, instead of crossing the event horizon, gets caught in these magnetic whirlwinds and is catapulted outward, perpendicular to the disk. These particles, electrons and protons, are accelerated along these narrow channels with such immense force that they are shot across space at over 99% the speed of light. The energy powering this launch is so staggering that it can overcome the black hole's own gravitational pull, turning the region around it from a simple drain into a complex engine with both an intake and an exhaust. The scale of these jets is almost impossible to comprehend. They can extend for hundreds of thousands, even millions of light years, far beyond the boundaries of their host galaxy. If such a jet were aimed at our solar system from a nearby galaxy, it would appear as a spear of light longer than the entire Milky Way. We can detect them because the particles within these jets, moving at such relativistic speeds, emit intense radiation across the electromagnetic spectrum, from radio waves to gamma rays, making them brilliant beacons visible across the cosmos. In some cases, these jets can even inflate gigantic bubbles of radio-emitting gas that loom over entire galaxy clusters, acting as cosmic weather systems that heat the surrounding gas and suppress the birth of new stars for eons. This demonstrates that a black hole's influence is not confined to its immediate vicinity. It can literally shape the evolution of the large-scale structure of the universe, proving that these objects are not just destructive voids but pivotal architects of the cosmic landscape. Yet for all their reputation as the ultimate voids of darkness, black holes are capable of becoming the brightest objects in the entire universe. This dazzling paradox is born from one of the most violent and energetic processes in nature, active feeding. When a black hole is not isolated but finds itself surrounded by a rich supply of gas, dust, or even an entire star, it transforms from a silent predator into a brilliant cosmic beacon. The key to this incredible transformation is the accretion disk, a whirling maelstrom of doomed matter that acts as the black hole's final feast before the point of no return. As material is drawn inexorably inward by the black hole's immense gravity, it doesn't fall straight in. Instead, it follows the conservation of angular momentum, much like water spiraling toward a drain. This incoming matter forms a flattened, superheated disk of plasma that rotates around the black hole at velocities approaching a significant fraction of the speed of light. The particles within this disk are packed so tightly and moving so furiously that they constantly collide with one another, generating immense friction. And as any physics student knows, friction generates heat, but this isn't the gentle warmth of rubbing your hands together. This is friction on a cosmic scale. The temperatures within the inner regions of a powerful accretion disk are almost incomprehensible, soaring to millions of degrees. At such extreme energies, the matter doesn't just glow with visible light. It radiates across the entire electromagnetic spectrum, from low-energy radio waves to the most powerful X-rays and gamma rays. The process is astoundingly efficient at converting mass into energy. While nuclear fusion in a star like our Sun converts less than 1% of mass into energy, the turbulent friction and magnetic fields within an accretion disk can convert up to 40% of the infalling matter's mass into pure radiation. This makes it the most efficient engine for energy production known in the universe. The result is a quasar or quasi-stellar object. From our perspective on Earth, a quasar looks like a single, incredibly bright star. But in reality, it is the blazing accretion disk of a supermassive black hole, often at the heart of a distant galaxy. This single point of light, smaller than our solar system, can outshine the combined light of every one of the hundreds of billions of stars in its host galaxy. It is a testament to the sheer power unleashed when gravity and matter collide in their most extreme form. So, while the black hole itself remains forever dark, its dining habits can light up the cosmos, making these invisible giants some of the most visible and spectacular objects across the vast expanse of space and time. While the black holes we've encountered so far are cosmic giants with masses ranging from stars to billions of suns, the laws of physics don't prohibit the existence of their polar opposites, black holes so small they could fit on the head of a pin. These theoretical objects are known as micro-black holes or quantum black holes, and their potential existence pushes our understanding of the universe into incredibly strange and exciting new territories. According to Einstein's general relativity, any amount of mass can become a black hole if you compress it enough. For a micro-black hole, we're talking about compressing a truly minuscule amount of matter into an unfathomably small volume. To create a black hole with the mass of, say, a mountain, you would need to crush all that matter into a space smaller than an atom. The forces required for such compression are almost unimaginable, far beyond anything we find in the modern universe. But there are two scenarios where such extreme conditions might occur, and both could open doors to new physics. The first scenario is one we can actually test here on Earth, inside the most powerful particle accelerators ever built. The Large Hadron Collider, or LHC, smashes protons together at velocities incredibly close to the speed of light. The goal is to recreate for a split second the kind of energy densities that existed just after the Big Bang. Some theories, particularly those involving extra dimensions of space, suggest that at these tremendous energies, the colliding particles could be squeezed together so tightly that they might briefly form a microscopic black hole. Now, before any concerns arise, it's crucial to understand that such an object would be utterly harmless. If formed, it would evaporate in a spectacular flash of energy via Hawking radiation in a timescale so short it's almost impossible to measure. Something like 10 to the negative 23 seconds. It would be gone before it could interact with even a single other atom. So far, the LHC has not found any evidence for these fleeting black holes, but the very fact that we can even conduct such an experiment is a testament to how far we've come in our quest to understand the fabric of reality. Not finding them is also valuable, as it helps us rule out certain models of extra dimensions and refine our theories of quantum gravity. The second, and perhaps more compelling, possibility is that micro-black holes are not something we create, but something we discover ancient relics from the birth of the cosmos known as primordial black holes. Unlike stellar black holes, these wouldn't have formed from the collapse of massive stars. Instead, they could have been born in the incredibly hot, dense soup of the early universe mere moments after the Big Bang. During this period of rapid expansion, random quantum fluctuations in density could have been magnified to macroscopic scales. In some tiny regions, matter may have been packed so densely that it collapsed directly under its own weight, forming black holes of virtually any size. A primordial black hole with the mass of a small asteroid could have a size smaller than an atomic nucleus, making it effectively invisible to most of our detection methods. Yet, according to this theory, such an object could still be drifting through our solar system right now, even passing through your body without you ever noticing, its gravity too weak to have any measurable effect. The detection of even a single micro-black hole, whether primordial or created in a lab, would be a revolutionary event for physics. It would provide the first direct experimental evidence for Hawking radiation, confirming Stephen Hawking's brilliant prediction and giving us a crucial window into the elusive theory of quantum gravity. It could also serve as stunning evidence for the existence of extraspatial dimensions, a key feature of string theory which would lower the energy required to form such objects. Finding a primordial micro-black hole would be like holding a fossil from the universe's first second of existence, offering us a direct probe into conditions we can only otherwise theorize about. These tiny titans, hidden in the quantum foam or wandering the galaxy, represent a frontier where the cosmic scale of general relativity and the bizarre rules of quantum mechanics finally meet, promising to unravel secrets about our universe that we are only just beginning to imagine. This dynamic role as a cosmic regulator is one of the most profound ways black holes shape the universe we see today. Far from being passive residents, supermassive black holes actively govern the life cycle of their host galaxies through a process known as feedback. This intricate dance between destruction and creation begins when the black hole is actively feeding. As vast amounts of gas and dust spiral inward, forming a brilliant accretion disk and powerful jets, the black hole unleashes a hurricane of energy back into its surroundings. This energetic output can have two seemingly opposite yet equally vital effects. It can violently suppress star formation, or it can paradoxically trigger it. The most common form of feedback is negative, acting as a cosmic quarantine that prevents a galaxy from growing too large. In the early, gas-rich stages of a galaxy's life, there is enough raw material to form stars at a ferocious rate for billions of years, which would eventually lead to overly massive and unstable galaxies. The central black hole acts as a built-in thermostat to prevent this. When it feeds, the tremendous radiation and relativistic jets blast outwards, heating the surrounding galactic gas and driving powerful winds. Imagine a colossal hurricane sweeping through the galaxy's reservoir of star-forming fuel. This superheats the gas, preventing it from cooling down and collapsing into the dense clouds required to birth new stars. In extreme cases, these winds can even blow the gas completely out of the galaxy, starving it of the material needed for future generations of stars. This feedback loop is beautifully self-regulating. The more gas the galaxy provides, the more the black hole eats, and the more energy it releases to shut down the very star formation that might eventually feed it. This process is why we don't see galaxies of infinite size and explains the observed correlation between the mass of a galaxy's central black hole and the mass of its central bulge of stars. The black hole literally sets the limit for its host's growth. But in a stunning twist, the same violent processes can also have the opposite effect, becoming a catalyst for creation. While the broad, energetic outflows from a black hole can heat gas on a galactic scale, the smaller scale interactions within those outflows can create perfect pockets for star birth. When the powerful jets from a supermassive black hole plow into much denser clouds of gas on their way out of the galaxy, they don't always just blow them apart. The leading edge of this jet can act like a cosmic plow, compressing the cold gas at its periphery. This shock compression squeezes the gas to incredibly high densities, crossing the critical threshold needed for gravitational collapse to begin. Essentially, the black hole's jet can trigger a stellar baby boom on its outskirts by creating intense pressure waves that rip through galactic nebulae. We have even observed this spectacular phenomenon in action. In a galaxy called Messier 87, home to the first black hole ever imaged, astronomers have found evidence of young, massive stars forming along the length of its powerful jet far from the galaxy's core. These stars are being born in a seemingly impossible environment, right in the path of a torrent of high-energy particles. It's a testament to the dual nature of these cosmic engines. They are both destroyers and creators, capable of sterilizing entire galaxies while simultaneously sowing the seeds for new solar systems in their wake. This complex feedback mechanism, balancing furious energy with delicate compression, ensures that galaxies evolve in a structured way, preventing chaos and fostering the long, sustainable cycles of star formation that make life-bearing planets like Earth possible in the first place. But perhaps the most radical and mind-expanding idea to emerge from this puzzle is the holographic principle, a concept that suggests our perception of a three-dimensional universe might be a magnificent illusion. This theory proposes that all the information needed to describe everything within a volume of space, every star, every planet, every person, might actually be encoded on the two-dimensional boundary that surrounds it like a cosmic projector screen. Think of the security hologram on your credit card. It's a flat, two-dimensional surface, but it creates a stunningly realistic image that appears to have depth and volume. The holographic principle applies this same idea to the entire universe, suggesting that the three-dimensional reality we experience could be a projection of information stored on a distant, two-dimensional surface. Black holes are the crucial test case that makes this wild idea so compelling to physicists. Remember the information paradox. What happens to the information about an object that falls into a black hole? The holographic principle offers an elegant, if bizarre, solution. It posits that the information isn't lost inside the singularity. Instead, when something crosses the event horizon, all the information that defined it, its composition, its structure, its history, is not destroyed but is rather transferred and imprinted onto the event horizon itself. Each tiny unit of area on the horizon, a Planck length squared, is thought to hold a single bit of information. The infalling object doesn't vanish, it merely adds its data to this incredibly complex, scrambled pattern on the surface. The black hole's interior, with its seemingly deep volume, is effectively defined by the information on its surface. It's a universe in a nutshell, with all its contents described on the shell. This isn't just a convenient metaphor to solve a paradox, it has profound implications for the fundamental nature of reality. If the holographic principle is correct, it means that the universe operates with a form of cosmic data compression. We may be living in a reality that has far fewer true degrees of freedom than it appears, a projection whose resolution has a fundamental limit. The world we see and feel in 3 spacious dimensions could be akin to a magnificent dynamic hologram, with the true underlying code of the universe existing on a vast 2-dimensional surface at the edge of the observable cosmos. This idea forces us to question the very nature of existence, space, and time, suggesting that our intuitive understanding of the world is a useful but ultimately limited interface. Black holes, these ultimate paradoxes, are therefore not just destructive ends but perhaps the key to understanding the very source code of the universe, pushing us to consider that reality might be far stranger and more interconnected than we ever dared to dream. And this profound connection between gravity and thermodynamics leads us to one of the most surprising and elegant facts about these cosmic giants. They are not cold, dead voids but possess a temperature. This revelation, which emerged from the brilliant work of Stephen Hawking, completely overturned our classical understanding and tied black holes directly to the quantum world. We're used to thinking of temperature as a property of objects with particles jiggling around. The hotter something is, the more its atoms vibrate. A black hole, by its very definition, was thought to be the ultimate absence of such activity, a perfect absorber that could never emit anything. Hawking's genius was to ask what happens when you apply the bizarre rules of quantum mechanics to the very edge of this perfect absorber. The key lies in the quantum foam, the seething, chaotic nature of the vacuum of space itself. According to quantum theory, empty space is not truly empty. Everywhere and at all times, pairs of virtual particles are constantly flickering in and out of existence. These particle-antiparticle pairs borrow energy from the universe for an impossibly brief moment, mandated by the Heisenberg uncertainty principle, before they inevitably collide and annihilate each other, returning the energy and vanishing without a trace. Normally, this process is perfectly balanced, creating no net energy. But Hawking realized that if this particle pair creation happens right at the precipice of an event horizon, the delicate balance can be shattered. There's a chance that one particle will fall into the black hole while the other escapes into space. The particle that falls in carries negative energy, which effectively reduces the black hole's mass by a tiny amount. Its partner, now free and unable to annihilate, becomes a real particle and flies off into the universe carrying positive energy. To a distant observer, this steady stream of escaping particles looks exactly like thermal radiation, heat emanating from the black hole itself. This is Hawking radiation, and it means that black holes are not black at all. They glow with a faint, cold light. The temperature of this Hawking radiation is incredibly low for the black holes we typically discuss. For a stellar mass black hole, the temperature is just a few billionths of a degree above absolute zero, making it far colder than the cosmic microwave background radiation that permeates all of space. This is why we have never directly observed this radiation. It is utterly swamped by the background noise of the universe. But the true astonishment comes from the relationship between a black hole's mass and its temperature. They are inversely proportional. The larger and more massive a black hole is, the colder it is. A supermassive black hole like Sagittarius, a star, is an incredibly frigid object. Conversely, the smaller a black hole is, the hotter and brighter it glows. A black hole with the mass of a small asteroid would be white-hot, emitting a torrent of radiation, while a microscopic one would be intensely hot, evaporating in a spectacular flash of energy. This thermodynamic property is what ultimately gives black holes a finite lifespan. The Hawking radiation process slowly bleeds away their mass and energy over cosmic timescales. For a solar mass black hole, the evaporation time is an almost unimaginable number, 10 to the 67 years, far longer than the current age of the universe. But for a hypothetical, tiny primordial black hole, the end could come much sooner in a final, explosive burst. This connection to temperature and thermodynamics isn't just a curious footnote. It's a profound bridge linking the worlds of gravity, quantum mechanics, and thermodynamics, suggesting that black holes are not mere oddities but fundamental objects that may hold the key to a deeper, unified understanding of the laws that govern our universe. And this astonishing warping of time opens the door to one of the most incredible theoretical possibilities in all of physics: the potential for a black hole to act as a natural time machine to the future. This isn't the science fiction trope of a metallic chamber whirling through a vortex. It's a direct and profound consequence of Einstein's theory of general relativity, which tells us that gravity doesn't just bend space, it also stretches time. The stronger the gravitational field you're in, the slower your clock ticks relative to someone in a weaker field. Nowhere is this effect more extreme than in the vicinity of a black hole, where gravity reaches its ultimate expression. To understand how this could work, let's craft a hypothetical mission. Imagine a courageous team of astronauts aboard an incredibly robust spacecraft, designed to withstand the ferocious tidal forces, who embark on a journey to orbit a stellar mass black hole at a meticulously calculated safe distance. Their mission is not to cross the event horizon, but to use the black hole's immense gravity as a gravitational anchor, allowing them to ride the extreme curvature of spacetime itself. From the perspective of the astronauts inside their ship, everything would feel perfectly normal. Their hearts would beat at a regular rhythm, their conversations would flow at a normal pace, and their ship's clock would tick off the seconds, minutes, and hours just as it always had. They would experience the passage of time in a completely ordinary way. However, for everyone back on Earth, something truly miraculous would be happening. The signals sent from the ship would begin to arrive slower and slower, their frequency dropping due to the intense gravitational redshift. To mission control, watching on their monitors, the crew's movements would appear to gradually slow down, like a video playing at a fraction of its normal speed. A single hour for the astronauts, measured by their own clocks, could correspond to days, years, or even decades passing on Earth, depending on how close they dared to orbit. This isn't an illusion or a trick of light. It is a fundamental difference in the actual passage of time caused by the severe warping of space-time. The astronauts are, for all intents and purposes, traveling into the future at an accelerated rate. After completing their 2-year mission from their own perspective, the crew would fire their engines and return to Earth, but upon their arrival, they would find a planet that had advanced centuries or millennia into the future. They would have aged only 2 years, while everyone they ever knew would be long gone, and human civilization would be utterly transformed. This is time travel to the future in the most literal sense, made possible by using the black hole as a natural accelerator for time dilation. Of course, the practical challenges are, to put it mildly, immense. The energy required for such a journey, the navigation around the accretion disk, and surviving the radiation environment make it a purely theoretical concept for now. But as a thought experiment, it stands as a powerful testament to the strange and wondrous nature of our universe, where the most exotic phenomena are not magic, but simply physics operating under conditions far more extreme than we experience on our pale blue dot. Yet for all their destructive power, black holes might harbor the most profound creative potential imaginable, the possibility that each one is a cosmic doorway to an entirely new universe. This idea stretches the boundaries of theoretical physics and human imagination, suggesting that these gravitational behemoths are not endpoints but rather catalysts for cosmic birth. The theoretical basis for this mind-bending concept often traces back to the mathematics describing what happens at the very core of a black hole. In Einstein's general relativity, the equations predict a singularity, a point where density becomes infinite and the laws of physics break down. But many physicists see this not as a physical reality, but as a sign that our current theories are incomplete. When we try to merge general relativity with quantum mechanics, some models suggest that the intense gravitational collapse might not end in a singularity. Instead, it could lead to a bounce, an event where spacetime undergoes such a profound transformation that it effectively gives birth to a new, expanding universe inside the black hole. Think of it like a cosmic Russian doll. From our perspective, we see a black hole as a region of spacetime from which nothing can return. But on the other side of the event horizon, the incredible warping of space and time might create the conditions for a new Big Bang. In this scenario, the matter and energy that fall into a black hole don't just vanish into nothingness. They become the raw material for an entirely new cosmos, expanding into its own dimensions, governed by its own physical laws. This newborn universe would be completely disconnected from our own. Its space-time would be expanding in a direction we cannot access or observe, making it a separate, closed-off reality. The black hole's event horizon then becomes the point of separation, the ultimate one-way door not just out of our universe but into another one. This leads to an even more staggering implication. If black holes in our universe can spawn new universes, could it be that our own cosmos began this way? The cyclic model, or the theory of cosmological natural selection, proposes that our universe might itself be the interior of a black hole existing in a larger parent universe. In this view, the Big Bang was the bounce that initiated our expansion from within a black hole singularity in another cosmos. This creates a breathtaking and humbling chain of creation. Every black hole in our universe could potentially be a separate universe unto itself, and our entire reality might just be one branch on an infinite fractal tree of cosmos within cosmos. The laws of physics in our universe, the constants like the speed of light or the strength of gravity, might not be fundamental truths but rather inherited traits, determined by the specific conditions of the black hole collapse that gave us birth. This could even offer an explanation for why our universe seems so finely tuned for life. If countless universes are being constantly spawned with slightly different physical parameters, it's no surprise we find ourselves in one where those parameters allow for stars, planets, and life to form. While this remains a highly speculative frontier of cosmology, it is grounded in serious mathematical exploration by respected physicists. It transforms black holes from terrifying endpoints into cosmic wombs, suggesting that death and rebirth on a universal scale are inextricably linked. It means that the ultimate fate of matter swallowed by a black hole might not be oblivion, but reincarnation into an entirely new existence, fueling an endless cycle of creation that plays out across the multiverse. Yet for all their seeming permanence and invincibility, black holes are not the eternal prisons of classical physics. They have a surprisingly poetic and profound expiration date, a fate dictated not by gravity but by the ghostly hand of quantum mechanics. This ultimate destiny was revealed by Stephen Hawking, who discovered that black holes slowly, imperceptibly evaporate over timescales so vast they defy human imagination. The engine of this evaporation is Hawking radiation, a process that begins at the very edge of reality itself, at the event horizon. In the quantum vacuum, pairs of virtual particles and antiparticles constantly flicker into and out of existence, borrowing energy from the universe for a fleeting moment before annihilating each other and returning it. This frenetic activity happens everywhere all the time, but when this quantum fluctuation occurs right at the precipice of a black hole's event horizon, the delicate balance can be shattered. One particle of the pair might fall across the boundary, forever lost to the singularity, while its partner escapes into the universe. The escaped particle becomes real, carrying positive energy away from the black hole. To conserve energy, the particle that fell in must have negative energy, which effectively reduces the black hole's mass by a tiny amount. To a distant observer, this stream of escaping particles looks exactly like a faint emission of thermal radiation heat coming from the black hole itself. This process is agonizingly slow for any black hole we can observe. The temperature of the Hawking radiation is inversely related to the black hole's mass. A typical stellar mass black hole with several times the mass of our Sun has a temperature of only a few billionths of a degree above absolute zero. This is far colder than the cosmic microwave background radiation that fills the universe, meaning that currently, for all practical purposes, these black holes are absorbing more energy from their surroundings than they are losing, causing them to grow, however slowly. But the universe is changing. In about 10 to the power of 100 years, a number so large it is essentially meaningless to the human mind, the universe will have expanded so much and cooled so dramatically that the background temperature will plummet towards absolute zero. It is at this point in the cold, dark, and incredibly distant future that Hawking radiation will become the dominant process and black holes will begin to lose mass in earnest. As a black hole evaporates, a fascinating and counterintuitive thing happens. It actually heats up, since the temperature is inversely proportional to its mass. As the black hole gets smaller, its temperature increases and the rate of Hawking radiation accelerates. The evaporation is a slow drip at first, but it becomes a steady stream, then a torrent, and finally a catastrophic cascade. In the final second of a black hole's multi-trillion-year life, its temperature soars to billions of degrees, and it releases the energy equivalent of 1,000,001 megaton hydrogen bombs in a blinding flash of gamma rays and elementary particles. And then it is simply gone. All the mass, all the energy, everything that ever fell into it is returned to the universe as radiation. According to our current understanding, nothing is left behind. The ultimate fate of a black hole is not a silent, cold remnant, but a spectacular, explosive finale that marks the end of its gravitational reign. This revelation completely transforms them from permanent fixtures into dynamic, evolving entities with a life cycle that ends not with a collapse, but with a silent, quantum whisper that echoes across an almost endless void. Yet for all their invisibility, the universe leaves behind a wealth of clues, and astronomers have become master detectives, piecing together the presence of these dark giants by observing the subtle, and sometimes dramatic, ways they interact with their surroundings. The most straightforward method is to simply watch how stars behave. In regions where a black hole is suspected, like the center of our own galaxy, astronomers can track the orbits of individual stars over many years. These stars are not moving in calm, predictable ellipses. They are whipping around an unseen point at breathtaking speeds. By meticulously charting their paths, just as Kepler did with the planets centuries ago, scientists can apply Newton's laws of gravity to calculate the exact mass of the invisible object tugging on them. The incredible velocity of a star like S2, which orbits our galactic center at over 15 million miles per hour, allows for a precise measurement, revealing the 4 million solar mass behemoth we call Sagittarius a star, all without ever seeing the object itself. It's a celestial game of tag where we only see one player, but their frantic movements give away the position and strength of their invisible partner. When a black hole is not alone but is actively feeding, it announces its presence with a brilliant beacon of high-energy light. This is where X-ray astronomy comes into play. As matter from a companion star or a gas cloud spirals into the accretion disk, It is heated to millions of degrees, causing it to glow not in visible light but in X-rays. Space-based telescopes like Chandra and XMM Newton are our eyes for this energetic universe, scanning the skies for these intense point sources of X-ray emission. In a binary star system, this can create a distinctive flickering signature as gas is steadily siphoned off from the visible star and superheated just before it vanishes across the event horizon. Sometimes the flow of matter can even become choked, leading to incredible X-ray outbursts that briefly outshine entire galaxies. By analyzing the spectrum and behavior of this light, astronomers can not only locate a black hole but also estimate its spin and rate of consumption, turning a destructive process into a valuable source of cosmic information. On a much larger scale, the sheer gravitational weight of a black hole warps the very fabric of spacetime around it, bending the path of light from distant objects in an effect known as gravitational lensing. This phenomenon acts as a natural magnifying glass. If a black hole passes directly between Earth and a distant star or galaxy, its gravity will distort and amplify the background light, often creating multiple images or a characteristic brightening called a microlensing event. While this is a rarer and more transient way to detect a black hole, it is incredibly powerful because it works regardless of whether the black hole is actively feeding or is completely dark and isolated. By monitoring millions of stars for these telltale flashes, astronomers can conduct a census of otherwise invisible rogue black holes drifting silently through the galactic halo, providing crucial data on their population and distribution. The pinnacle of this detective work, however, moved from inferring presence to confirming appearance with one of the most ambitious experiments in scientific history, the Event Horizon Telescope. This was not a single telescope, but a global collaboration linking radio observatories from the South Pole to Spain to Hawaii, effectively creating a virtual telescope the size of Earth itself. This incredible resolution was necessary to attempt the seemingly impossible, to image the shadow of a black hole's event horizon. In April 2019, the world watched in awe as the EHT team revealed the first ever direct image of the supermassive black hole at the heart of galaxy M87. That now iconic fiery ring of light wasn't the black hole itself, but the photons orbiting just outside the point of no return, outlining the dark shadow of the event horizon against the brilliant backdrop of its accretion disk. This monumental achievement was not just a pretty picture, it was a stunning validation of Einstein's theory of general relativity under the most extreme conditions and provided direct visual proof of the existence of these cosmic phenomena, transforming them from theoretical abstractions into observable realities. But to truly grasp the existential challenge of black hole presence, we must confront a question that seems deceptively simple. What does it even mean to be inside something? Our entire intuition about containment is built on a classical, three-dimensional worldview. A book is inside a box if it is surrounded by the box's walls. An apple is inside a bowl if it rests within its concave surface. This concept relies on a clear, stable separation between the container and the contained, between the interior and the exterior. A black hole, governed by the bizarre rules of general relativity, shatters this intuitive framework completely. The event horizon is not a physical surface you can touch. It is a mathematical boundary in space-time, a point of no return defined by gravity's ultimate triumph. Once something crosses this threshold, the very definitions of inside and outside undergo a radical transformation. According to Einstein's equations, all paths within the event horizon lead inexorably forward in time toward the central singularity. There are no paths that lead back out. This means that the interior of a black hole is not a static place you can occupy. It is more accurately described as a future. For any object that has crossed the horizon, its entire existence is now a finite journey along a timeline that terminates at the singularity. the spatial dimensions we are familiar with become fundamentally mixed with the dimension of time in a way that makes the concept of a navigable space inside almost meaningless. You are not in a location, you are on a one-way trip. This turns the classical idea of containment on its head. Instead of being inside a container, an object that falls into a black hole has had its future causally separated from the rest of the universe. The inside is not a separate place within our universe so much as it is a separate fate. This leads to some physicists proposing even more radical interpretations. The black hole complementarity principle, for instance, suggests a profoundly strange duality. From the perspective of an outside observer, an object falling into a black hole never actually crosses the event horizon due to the infinite time dilation. Instead, its information gets smeared and encoded onto the horizon's surface in a scrambled, hot layer of quantum information. However, from the perspective of the object itself, it passes smoothly through the horizon and continues inward. Both perspectives could be correct within their own frames of reference, meaning the object is both vaporized on the surface and traveling through an interior simultaneously. There is no single objective inside that all observers can agree upon. The reality of containment depends entirely on who is doing the observing. Pushing this idea even further, some interpretations of quantum gravity and string theory propose that the interior of a black hole might not even be part of our universe's spacetime continuum at all. The mathematical models suggest that the extreme warping of spacetime at the singularity could create a bridge or Einstein-Rosen wormhole to another region of spacetime or even to a completely different universe. In this view, the inside of a black hole is merely a tunnel, a transient, non-physical throat connecting two separate realities. The matter that falls in isn't contained, it is transferred. This transforms the black hole from a cosmic prison into a potential gateway, challenging the very notion of a localized interior by suggesting it is just a brief passage to an entirely different existence, making the concept of inside not a destination but a corridor to somewhere else entirely. But the sheer violence of the gravitational gradient is merely the opening act. The environment surrounding a black hole is a cosmic pressure cooker where every known force is amplified to its absolute extreme. Within the churning maelstrom of the accretion disk, matter doesn't just heat up. It becomes a plasma so energetic that atoms are torn apart into their fundamental particles, swirling in a chaotic soup at temperatures of millions of degrees. This isn't a calm, orderly rotation. It's a frenzy of collisions and friction that generates not just intense heat, but also unimaginably powerful magnetic fields. These fields, wound up tighter and tighter by the black hole's immense spin, become the dominant architects of chaos, channeling this superheated plasma into colossal jets that fire out from the poles at nearly the speed of light. The energy contained within these magnetic structures is so vast that it can literally rip apart atoms and accelerate particles to energies that dwarf anything our most powerful particle colliders on Earth can ever hope to achieve. It's a perpetual storm of cosmic proportions where magnetic forces don't just guide matter, they utterly control it, creating structures that can span millions of light years and shape the evolution of entire galaxies. This extreme environment also serves as the ultimate laboratory for probing the most profound mysteries of physics, forcing the two great pillars of modern science, general relativity and quantum mechanics, to collide. The region just outside the event horizon is where the bizarre, probabilistic world of the quantum meets the overwhelming force of gravity. Here, the phenomenon of Hawking radiation is born from the quantum foam, where virtual particle pairs flicker into existence only to be torn apart by the black hole's gravitational pull. This process is a direct and observable consequence of quantum effects playing out on a gravitational stage of epic proportions, offering a unique window into how these two theories might be unified. Furthermore, the mind-bending time dilation near a black hole means that quantum processes, which normally occur in fleeting fractions of a second, could be stretched out and observed from a safe distance, allowing us to study their behavior in slow motion under conditions of immense gravity. It is a natural experiment on a grand scale, testing the limits of our knowledge and providing clues to a deeper, more complete theory of quantum gravity that has eluded physicists for decades. Perhaps most astonishingly, the very center of a black hole, the singularity, represents the ultimate frontier of extreme physics, a place where the known laws of the universe break down completely. According to general relativity, all the matter that falls into a black hole is crushed into a point of infinite density, where the curvature of spacetime becomes infinite and our mathematical models simply fail. This isn't just a very small, very dense object, it is a boundary beyond which our current understanding cannot pass. This makes the black hole's core the most extreme laboratory imaginable, a place where the very concepts of space and time as we know them cease to have meaning. Theorists propose that here, at the singularity, we might find evidence for exotic new physics like strings, loops, or other quantum structures that could reveal the fundamental building blocks of reality. By studying the effects a black hole has on its surroundings, from the way it lenses light to the gravitational waves it emits when it collides with another, we are indirectly probing the nature of this mysterious heart, using the cosmos itself as our experimental apparatus to explore realms of energy and density that are forever beyond our physical reach here on Earth. Yet for all their immense gravitational pull, black holes exert an even greater force on the field of theoretical physics itself, drawing us toward a confrontation with the greatest challenge in modern science. These cosmic paradoxes are far more than just fascinating objects. They are the ultimate natural laboratory, the one place in the universe where the two most successful but utterly incompatible theories, general relativity and quantum mechanics, are forced to collide. General relativity gives us a breathtakingly accurate description of gravity as the curvature of spacetime on large scales, perfectly predicting the orbits of planets and the bending of light around a black hole. Quantum mechanics, on the other hand, provides an equally powerful framework for the bizarre, probabilistic behavior of matter and energy at the smallest scales. The problem is that these two pillars of physics speak different mathematical languages and operate under fundamentally different rules. They work flawlessly in their own domains, but when their domains overlap, as they must at the center of a black hole, the result is a cacophony of contradictions and infinities. The heart of this conflict is the singularity. General relativity predicts a point of infinite density where the laws of physics break down, but quantum mechanics abhors such infinities and insists that information can never be truly lost. This is the core of the information paradox, a problem so deep that its resolution is expected to rewrite our understanding of reality. To solve it, we need a theory of quantum gravity, a single framework that seamlessly unites the force of gravity with the quantum world. For decades, this has been the holy grail of physics, and black holes are the unique environment where the clues to this theory are hidden. The event horizon is the stage where the quantum vacuum interacts with the strongest possible gravitational field, producing Hawking radiation. The singularity is the realm where the very concepts of space and time must be reimagined through a quantum lens. By studying these effects, we are conducting a natural experiment that we could never hope to replicate on Earth, using the cosmos itself to guide us toward a deeper truth. Several promising candidates for this unified theory are being tested against the harsh light of black hole physics. String theory, for instance, proposes that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings. In this view, the black hole singularity might be replaced by a dense, fuzzy ball of these strings, preventing the infinities predicted by classical theory. String theory also offers a compelling solution to the information paradox through the holographic principle, suggesting that all the information about what fell into the black hole is not lost inside but is encoded on its two-dimensional surface. Another major approach, loop quantum gravity, suggests that spacetime itself is not smooth and continuous but is made of discrete, tiny loops woven into a fabric. This theory also avoids the singularity, proposing instead a quantum bounce that could transform the interior of a black hole into a gateway to another universe. The incredible detection of gravitational waves has now given us a powerful new tool to test these ideas. By carefully analyzing the chirp and ring-down signals from merging black holes, physicists can look for tiny deviations from Einstein's predictions. Does the final, vibrating black hole settle down exactly as general relativity says it should, defined only by its mass and spin? Or do we detect faint echoes or other subtle imprints that hint at quantum structure just outside the event horizon, a possible quantum hair that would revolutionize our understanding? Each new merger detected is like striking a bell and listening to its tone. The precise quality of that tone could reveal the fundamental nature of the bell's material. Finding even the slightest anomaly would be a monumental breakthrough, providing the first experimental evidence for quantum gravity. Ultimately, the quest to understand black holes is a quest to understand the universe at its most fundamental level. They are not merely destinations for matter, they are gateways to a new physics. Unlocking their secrets won't just tell us what happens at the center of a black hole. It will reveal the very rules that govern space, time, and existence itself, offering us a unified window into the cosmos from the smallest quantum flicker to the largest galactic structure. And now we arrive at a fact so astonishing it reframes our entire understanding of these cosmic giants, transforming them from monstrous anomalies into potential architects of existence itself. After a journey through infinite density, spaghettification, and the evaporation of spacetime, we confront a possibility that sounds like it's pulled from science fiction. Black holes might not just be compatible with life, they might be absolutely necessary for it. This idea rests on a profound understanding of cosmic ecology, the intricate web of cause and effect that connects the most violent events in the universe to the serene conditions on a planet like Earth. The first and most crucial role black holes play is that of the ultimate galactic regulator. As we've seen, supermassive black holes at the hearts of galaxies act like cosmic thermostats through a process of energetic feedback. In the early, chaotic universe, galaxies were saturated with gas, primed for an explosive era of star formation. Without a regulating mechanism, a galaxy would burn through its fuel too quickly, creating a brilliant but short-lived burst of massive stars that would rapidly go supernova, blasting the remaining star-forming gas away and leaving the galaxy a sterile, reddened relic. But a central black hole prevents this runaway consumption. When its feeding frenzy reaches a peak, the resulting radiation and powerful jets heat the surrounding gas, preventing it from cooling and collapsing into new stars. This feedback loop ensures that star formation proceeds at a steady, sustainable pace over billions of years, rather than in a single, furious burst. This longevity is essential for life. It provides the stable, long-term environment needed for solar systems like ours to form around a second or third generation of stars, stars that have been enriched by the heavy elements forged in the lives and deaths of those that came before. A galaxy without its central black hole would be a cosmic flash in the pan, likely incapable of fostering the long, slow, stable evolution that complex life requires. Beyond just regulating the pace, black holes are also cosmic distributors, essential for seeding the universe with the very building blocks of life. The elements crucial for biology, carbon, nitrogen, oxygen, and iron, are forged in the furnaces of stars and in the spectacular explosions of supernova. But simply creating these elements isn't enough. They need to be dispersed far and wide, mixed into the interstellar medium so they can be incorporated into new generations of stars and planets. This is where black holes, ironically, become incredible agents of creation. The relativistic jets that scream from their poles and the powerful winds blown from their accretion disks act like cosmic blenders and conveyor belts. They can scoop up enriched material from a galaxy's core and blast it out into the galactic halo and even beyond, spreading these vital elements throughout the galaxy and into intergalactic space. This process ensures that the ingredients for planets, oceans, and life itself are not locked away in the galactic center, but are made available everywhere. Some theories even suggest that the shock waves from these outflows as they plow into distant gas clouds can trigger the formation of new stars and planetary systems already pre-loaded with a rich supply of heavy elements. In this way, the most destructive force in the galaxy is also a vital gardener, sowing the seeds for future worlds across the cosmic landscape. This leads to a final, breathtaking consideration about the very structure of the universe that makes life possible. The mysterious substance we call dark matter provides the gravitational scaffolding for galaxies to form at all. And while its exact nature is still unknown, there is a compelling hypothesis that a significant portion of it could be made of primordial black holes. If this is true, then these ancient, invisible objects would have been the gravitational seeds around which the first stars and galaxies coalesced after the Big Bang. Without their initial pull, the distribution of matter in the universe might have been too smooth, preventing the clumping necessary to form the galaxies that host stars and planets. So, in a very real sense, if primordial black holes are a component of dark matter, then we owe the very existence of our galactic home to them. From the largest scales of cosmic structure to the sustainable pace of star formation and the distribution of life's essential elements, black holes are woven into the story of our existence. They are the terrifying, dark engines that, through their immense and violent power, have helped create a universe that is, against all odds, capable of wondering about them. So after this incredible journey through 30 mind-altering facts, what's the final takeaway? It's this: our perspective on black holes has been completely transformed. We began by seeing them as the universe's ultimate monsters, simple cosmic vacuum cleaners lurking in the void, hungry for destruction. But now we understand they are so much more. They are dynamic engines, brilliant beacons, cosmic regulators, and perhaps even cosmic gateways. They are not the end of physics, but the beginning of a deeper understanding. They challenge our most fundamental ideas about reality, forcing us to question the nature of space, time, information, and existence itself. Every fact we've explored peels back a layer of the cosmic onion, revealing a universe that is far stranger, more interconnected, and more wondrous than we ever imagined from our small corner of it. This transformation in understanding is what makes the study of black holes so vital. It isn't just an academic exercise for astronomers in ivory towers. It is a fundamental human endeavor to push the boundaries of knowledge. By staring into these abysses, we are ultimately staring into a mirror, reflecting our own quest for understanding. Each paradox they present, from the information dilemma to the nature of the singularity, is a puzzle waiting for its solver, a future Einstein or Hawking who might one day unite the laws of the very large with the laws of the very small. This pursuit expands human consciousness itself, reminding us that curiosity is our greatest tool. The universe is under no obligation to make sense to us, yet we continue to ask, to probe, and to listen to the faint whispers of spacetime, driven by the profound need to know our place in the cosmos. And this journey is far from over. In fact, it's accelerating. With every new gravitational wave detection, every exquisite image from the Event Horizon Telescope, and every daring new theory, we are getting closer to unlocking the next great cosmic secret. The mysteries of dark matter, the true nature of the Big Bang, the possibility of other universes, black holes sit at the heart of these questions, and answering them will redefine reality for generations to come. The greatest discoveries are still out there, waiting in the dark, So keep looking up, stay curious, and never stop wondering about the magnificent, mysterious universe we call home. If you want to join us as we continue to explore these cosmic frontiers, make sure to subscribe and hit the bell so you don't miss our next journey into the unknown. The universe has endless stories to tell, and we're just getting started.